Welcome to the Knowledge Graph seminar. Today, we are in the week 10, the final week of the seminar. We've had a very interesting series thus far. So this week, we are going to conclude the series. And today, we want to present to you a survey of implementation tools for building knowledge graphs. This is a question we've had quite often. People have appreciated the overview and the concepts and the theories that we've covered in the seminar until now, but then people want to know how should they get started on a project? What options do they have? What software implementation platforms are there? And Naren is going to give us a very good overview of that. And after his portion, I'm going to take 10-15 minutes to summarize the series and give you some key takeaways, especially along the theme of what's new about knowledge graphs. Because many times people say that, oh, this is just old semantic networks rehashed. But there is definitely some new development, some innovation here, and I'll like to present to you my perspective on that. Okay, so let's get started with the first part of the presentation. Naren, over to you.
Thanks, Vinay. Let me share my screen. Cool, and there's a present button here. Okay.
Looks good.
Can you all see it? Okay, sounds good. The usual stuff, these are my own views, not related to my employer. I don't have any affiliation to any of these software, but I'm a fan of many of these. Just very impressed how amazing some of these open source projects are. So these are the rough topics I will be going through today. I think architecting software is very different today. It's all about reuse of code rather than writing from scratch. And typically for knowledge graphs, since it's a highly processed structured data structure, you have to go typically through these steps. You have to join a lot of data sources. Sometimes you have to join lists. Sometimes you have to join, you have to extract information from unstructured pieces like news articles, etc. And after you do a lot of processing, you store it in graph databases for retrieval. And then there's another class of software called graph compute engines, which are great for doing large scale computations over graph. So I will go through all of them. It'll be a whirlwind tour of all these categories. It'll sort of be breadth first search. I won't go into too much depth. Hopefully we can have a lot of questions during this session, and then we can spend a lot of time answering those questions. So what is different about architecting software today? So a lot of things have changed. When I first graduated from college way back in 1997, it was all about how many lines of code I wrote. How are you writing these thousands of lines of code? That was a typical question in interviews. And now it's the reverse. How many packages have you reused? How can you get efficient use of, how can you create software with efficient use of all that's available out there? And I think the overall strategy is to decompose a high level problem into smaller components and then map each component, subcomponent into some software package that you can find from the open source world or something, or vendor or something like that. And then you write a lot of code to configure and glue all these pieces together. So I think you need maturity in mapping a subcomponent to a particular package. Then you need understanding to configure and glue them together. And due to this is, I think, a very good problem to have is there are too many options for open source packages these days. And then it's a search ranking like problem. Then you need your own ranking function around, okay, is it a reputed source? How many stars, forks, all these kinds of metrics. And then you can make an informed decision about which packages to use. Cool. So first, let's come to the first two topics, like joining data and from lists and joining and extracting information from unstructured sources. So let me look at my notes. Cool. So typically to create knowledge graphs, this is a very common task you have to do all the time. And Vinay covered this in one of the lectures, so I won't go into it into too much depth. But typically you need to join lists. Here's an example where we want to create a more comprehensive view about Apple and companies in general. And then what you do is you buy or you create lists from different sources, and then you need to match those lists. And the problem is there's no nice key to join these lists. And then if you just look at Apple Inc. and Apple computers here, you don't have enough information to say that they are the same record. But when you include address, for example, you become more and more confident about which records are actually talking about the same entity and which are not. So it's a very common task that you have to keep doing again and again. So what do? You find a list of, you look at the open source community for these record linkage software, and there are lots of them available. And this is one of the most comprehensive that I found. It's a package called dedupe. It's a native Python package, and it gives you very, very good programmatic access. So first of all, you define all your column names by these data types. There are these primitives like text, short text, date, time, etc. But there are even more semantic types, higher level data types like price, address, and then they give you a lot of different options to match each of those in a fuzzy way. So that's a very, very comprehensive package. You can even define your own types. You can even create your own matching algorithms. They provide a lot of inbuilt ones. For example, if you define something as lat long, if there's a business and there's a lat long column, it has a very nice metric on, I think it's called Haversine distance, which just doesn't calculate the Euclidean distance between the lat longs. It actually takes into account the curvature of the Earth as if it was a sphere. There are lots of different good matching and parsing techniques for addresses, names, etc. And if you remember, when I had taught you about blocking, they have lots of default blocking techniques. You can configure the blocking techniques. There are also 2 or 3 different kinds of matching techniques. If you have examples of which pairs, which records belong together or not, it will actually by default be able to learn a logistic classifier. And then you can, of course, update it with other sklearn methods, but it has some inbuilt. If you use it by default, it just calculates cosine distance, and then you have to give it a threshold. And then based on, if you have a UI or something like that, you can actually push it through their module for active learning. So you can learn a lot faster given a lot less examples, which the algorithm is not very confident about. Cool. So sometimes you can do everything with machine learning. There are a lot of cases where you cannot use machine learning. And you just have to, the easiest way might be to actually just write a set of rules. And person name matching is one sort of task we have encountered again and again, where you have to just say, you know what, let's just use a pre-created dictionary. So someone out there has created a very nice dictionary of nicknames, diminutive names, etc. for Western names. So it's quite comprehensive. So this is something that you have to use. There are other situations where you have names that are spelled in very different ways, and then you have to find some implementation of SoundX, or today they use like double metaphone is a very common algorithm. So to use these kinds of techniques to to transform these into phonetic representations, which will actually match. So this is a common thing that we've had to use. Here's a very nice package, nice table that someone has created. This user has created of most popularly used record linkage software. Look at all the sort of columns. Do they have APIs? Are there GUIs? Some of them have GUIs so that they can be used in a more efficient way. Linking, deduplication, supervised learning. So all these nice features. Cool. So next, let's come to unstructured data sources. So most of the world's information is, I think, present in the form of unstructured text, unstructured information like text, news articles, reports, emails, etc. And it's a pretty hard task to parse out information, do information extraction over this text, and turn them into knowledge graphs. In this space, I've really been quite pleased with an open source package called Spacey, which is an NLP software. Unlike NLTK, I think a lot of people have used NLTK. It's more for research purposes, gives you a lot of different options for putting in like 10 different types of taggers, tokenizers. It's a very good package for experimentation and learning, but Spacey has been optimized for like building actual real world software. So it has a lot of pre-built models for part of speech, NER, noun chunking. You can even create your own custom NER from, let's say you have a biomedical application or legal application, where you have different kinds of entities, like a molecule name or something like that. And, or the syntax of the English is different. Then you can build your own NER software, NER model right from scratch, or you can improve custom the existing NERs. And they have a very good tool, a UI tool called Prodigy, that you can build all these models really fast. So imagine you can employ a few users who can use this Prodigy UI. You can go through a few thousand examples really fast. And I think there's an active learning component built too. So this thing builds, this Prodigy will behind the scenes build the model as you are labeling examples, and then it selects examples where and prioritizes examples where the classifier is unsure. So this is a very good software for doing that. It also includes an entity linking framework. So we learned about entity linking in lecture, so I won't go to that. But Spacey also includes the entity linking framework. It's a framework. It does not actually link to a database, but someone out there, it's called Spacey Entity Linker. They have created a linker that maps to Wikidata. So it's pre-built on Wikidata, so you could use it quite, it's almost ready to get used. Cool, so that is about how to extract information from text. Oh, there's one more nice thing that Spacey offers is dependency parsing. So look at this sentence here. So if you want to learn more about dependency parsing, go take CS224S, Chris Manning's or Percy Liang's course, and it'll tell you all about dependency parsing. But essentially it creates this kind of, there's a graph structure right here. Look at this sentence, John married Jill in 1998. And you, just like a graph, it has edges, directed edges, they're labeled according to English grammar. And you can use all these signals to actually build and train a graph. In fact, if you look out there, you'll get a lot of implementations for subject, predicate, object, the triple extraction using Spacey dependency parsing. So, okay, cool. So someone out there has created a very good package called SpiceX, which is Spacey pipes for knowledge extraction. And it is a whole end-to-end pipeline to go from unstructured text all the way to building a graph called a wiki graph. That's their reference application, and they have included all these different components. So it's very new. So I encourage you to take a look at it. Now let's come to graph databases. So imagine you do all this work and massage and extract and process your lists, and then you augment all those that information with knowledge extracted from unstructured text, and now you have a knowledge graph representation. Now you have to actually store all this information in what is called a graph database. So graph database, very similar to SQL databases, are used for more online transaction processing than analytical processing. And I will cover the analytical processing in the next section, which is graph compute engines. So when choosing a graph database, there are lots of different dimensions in which you can evaluate them. What do they have a distributed implementation? Is there ACID? What are the query languages that it supports? Unlike SQL, there is no good standardization yet in the graph world. Recently, Cypher has been taking a little bit of lead, but still, I think like SQL, there is no clear winner or clear standard. Then for real world projects, there's a lot of other dimension. Is it managed? What is the pricing? What is the support ecosystem? Are there plugins available? Are there developers available to work on your project, support your project? So a lot of different dimensions. And then I will go through two of them actually. One is Neo4j. So Neo4j actually offers, so Neo4j is the most popular one that I've seen. And they have two versions. One is called a community version, which is open source. And then they have an enterprise version. And I won't go through too much depth. If you look at last year's course, you will actually find a very nice video by someone from Neo4j. So it's a property graph. It scales horizontally. It has a lot of access controls. I think they're node level and edge level access controls. So you can label these nodes and then give access controls that some users may not be able to see all the nodes. I think they're the ones who are the primary drivers of Cypher. They have good support for drivers connecting programmatically through different programming languages. They have a UI that comes over with it. If you go to the professional version, then you have a lot of options for managed failover, backups, all this. But I won't go into too much depth. I've given the link here so you can read more about it. Cool. So next is, since the cloud is so popular, I thought I'll just mention a few lines about Amazon Neptune. It is not open source, but if anyone here, a student here, or anyone is planning to, I know Stanford students are like one of the best entrepreneurs, and you might have an idea in mind. And if you do, and they need knowledge graphs or graph DBs, the Amazon Neptune is a good option to start off with. It's a relatively new offering. It is managed. It has both property graph and RDFs. It supports the Gremlin and Sparkle interfaces, query interfaces. It is ACID. There's continuous backup to Amazon S3. If your product has users across different parts of the globe, there is automatic replication between different zones. If you're dealing with sensitive data, it has encryption at rest, encryption in motion. If you're in an industry like finance, or regulated industry like finance or healthcare, there's automatic auditing from the logs that you can generate pretty good logs. And then those logs have a lot of information that you can use for auditing. In fact, they take a step even they take the next step and they have designed 3 common use cases based on graph databases. So identity and personalization, fraud detection, and knowledge graphs. So they have defined 3 products that have been built over the Amazon Neptune. So if one of them actually, if you can map your backend to one of these, then that's awesome. You can start using them, and the pricing is quite competitive. It might be the best and the most fastest way for you to launch something with lowest cost. Cool. So that was a section on graph databases. I'm doing a quick time check. Okay. So I'll go for around 10 or 20 more minutes. So graph compute engines are slightly different from graph databases. They are mostly used for doing heavy computations on graphs. So let's say you have your graph. Now you want to do like a very massive computation on it, like a page rank or community analysis, community detection. So there's a separate class of software that fall into this category, graph compute engines. Some like Neo4j, like if you look at Neo4j, they have a lot of features that actually put them into this category, graph compute engines, but typically they are different. So let me go through 2 of them that are quite well designed. One is like a very raw package called NetworkX. It's a Python package and very active package. Lots of contributors, stars, forks. It's all in memory. So you have to build a graph programmatically. Here's a small snippet of code that you see. And you have to literally write Python. If you're a good Python developer, you should go for this. It's in memory. It has a Python interface. It does not have a query language, etc., to query the graph. But if there are some other packages available which have created like a query language for that. And if you're a Python expert, it's very flexible. You can actually, if your Python class is hashable, etc., you can actually embed any kind of object into a node and an edge. It is rich, very, very rich in algorithms. So I'm going to actually click here to just show how many algorithms it has. Look at all the available algorithms that it has. It's just amazing, very impressive actually. Community detection, page rank analysis, so all sorts of things. So definitely use this package if you want a plain, very simple Python-based package. So next, okay, so here's a very good, let me see, yeah. So here's a very good demo that someone has created based on NetworkX and done community detection over. So this is a novel that you all know, Les Miserables. And then I think it's written by Victor Hugo. And then there's these are all characters in the novel. And then someone has actually created a co-occurrence matrix of characters that are mentioned in the same chapter. And then they've ran a community detection algorithm, and the colors represent those. And someone has created a really nice animation using a package called D3. And I'm mentioning D3 because it's again it's a JavaScript visualization software created by a Stanford grad. So let me this is the raw covariance matrix, and then using D3 has this visualization. I don't know if you can see all the nice animation, but you could actually do community detection and make this kind of a visualization quite easy.
So we could see the animation, but what is this animation actually showing?
So it is showing the following. From covariance matrix, it actually tries to guess based on which characters might all know each other and might be one community. And it colors them accordingly. And then this whole fancy animation is a very nice way to reorder the rows and columns so that all these communities, they appear together in this visualization. Was that clear? Or?
Yeah, I
Okay.
think that's clear. It
Cool.
sounds interesting. So, do you know if people have validated this? And
good question. I do not know, actually. I do not know how if people have validated, or all these sort of this group here, which is a community, actually know each other. I don't. Good question. I do not know that. But here they run the Louvain community detection algorithm to create these communities and sort of guess that these people might know each other. But that's a very good question, actually. We need someone to actually validate this. Cool. Okay, so NetworkX is great if you know Python really well. Your data set fits in one machine. What do you do if your data set is larger? What if you do if your knowledge graph is larger? Then I think you have a problem. It is very expensive to scale vertically. It's hard to buy machines with greater and greater RAM. And horizontal, you have to resort to horizontal scaling. So what do you do then? Apache Spark, which is one of the most popular parallel compute engines, parallel analytical engines, distributed analytical engines. It's sort of the next step from Hadoop. So the predecessor was Hadoop, and now people use Apache Spark, and Stanford has a good connection to Apache Spark. Matej Zaharia is one of the creators of Apache Spark. So you could use Apache Spark. Apache Spark has many different modules, one for machine learning, one for just database kind of operations. They have a module called GraphX, which is very suited for creating graph applications. And I found a couple of very good tutorials on the Stanford site that point you to Apache Spark, the whole Apache Spark, and specifically the GraphX module. So in Apache Spark, the main object or class is called the graph class, which extends their main class called an RDD, a resilient distributed database, which is their implementation of a distributed list. And there's lots of operators that they have defined on a graph. There are property operators, structural operators. Let's say you want to reverse your whole graph. You want to create a reverse page rank. So rather than reading your whole million node graph and then copying and creating one, there are very efficient parallel implementations of just going and reversing the edges in the graph and then so that you can calculate page rank, reverse page rank very efficiently. There are all these neighborhood operators. Imagine you have a Facebook graph and you want to quickly say, what is the average number of neighbors each user has? So you can use these operators. And the whole, I think the whole effort that Apache Spark GraphX guys have spent is in parallel implementations, very efficient implementations. On the ML side, they do not have too many algorithms. They just have PageRank and a personalized PageRank. In all these space of discrete algorithms, they just have 2 or 3. So not at all as rich as NetworkX, but if your graph is large, then I think you are probably stuck with something like Apache Spark. And for the students here, if you're looking for a project to contribute to, an open source project to contribute to, you might actually try to join this project and enrich their graph ML or just their graph algorithm package. Cool. So what's next on the list? So I've done with Apache Spark. Cool. So I think that's it. So let me actually recap what I took you through a lot of information. So I just told you about how software is architected today and how you look to the open source community in a very clever way to figure out how to map components then showed you some software on how to join lists, fuzzy joining of lists. Then I talked about dedupe, which is a very customizable package in Python. Then I talked about Spacey, which allows you to extract information from unstructured text, all the NER, the linking, how to build your own models using Spacey's UI called Spacey Prodigy. Then I talked a little bit about graph databases. And there I talked about Neo4j community, which is open source. And then I talked about a cloud managed product, Amazon Neptune. And then I talked about graph compute engines, where let's say you have a graph and you want to do this heavy analytical workload on it. So Apache Spark and NetworkX. This was a whirlwind tour of the most typically what the steps you will go through when you are creating a knowledge graph. So with that, I think I'm done with my talk. Vinay, over to you.
There are a couple of questions. We can just start. These two questions from Anand. How do we match the relationship between companies? For example, Cirrus Logic is a supplier of Apple. Shall we use dedupe or Spacey or entity linking or Wikidata or?
So you need some source to say that Cirrus Logic is a supplier of Apple. You need to look at news. Sometimes for important suppliers, Apple will mention that in their filings, in their financial SEC 10K or 8K, or Cirrus Logic might. If Cirrus Logic wants to, most of the time the smaller company mentions this larger company. So you have to actually look at these sources for this piece of information. There are a lot of vendors like FactSet who actually curate. They have a bunch of people who look at all these documents and they sell all this information. So you can, if you're using it for work or you can spend that amount of money, then you can even buy this information from vendors, or else you have to just look at news, run Spacey on it, run entity linking on it, run relationship extraction, etc., and create this on your own.
Right. So it seems that identifying whether somebody's a supplier of somebody else, that's not really a linking problem or dedupe problem, right? It's more of a sort of relationship extraction problem.
Yes, it's a relationship extraction problem. And then to strengthen the edge, to be really confident because the web does not contain curated information, then you have to look at lots of documents. And if there is strong evidence in multiple documents that Cirrus Logic is a supplier to Apple, then I think you can say, okay, I will curate this node. And when you look at multiple documents there, I think you might need to use dedupe or the string matching functionality of dedupe. You might need to use entity linking, etc.
Okay. And does Spacey provide you with a relation extraction library?
No. So they provide you the building blocks that you can use to extract relationships. So they provide, first of all, NER, noun chunking. And then they provide you the dependency graph. So you can walk the dependency graph and then you can establish your own, conclude your own relationships. And
okay. So means Spacey doesn't have a turnkey solution for relationship extraction. Is there another package that has that?
So I've seen, for example, there are some packages that do SVO, the subject, predicate, and object extraction. There are some, I've seen packages that do some kind of relationship extraction, but in my experience, none of them has been too good. So you have to actually train something on your data set.
Okay.
Simple challenges are the following. Let's say you train one on news articles, the body of the news article. But when you actually run it on a data set that has a different syntax, even if you run one that has been built on the news article body, and then you run it on the news article headline, it fails quite miserably because the grammar and syntax of the news headline is different. So most probably you will have to you take the software and train your own extractor. That is where I think the value lies.
Yeah. Okay. Then there's this question: can we use AWS Neptune, NetworkX, GraphX together? Is there a turnkey template for the end-to-end machinery to launch a KG-based system?
Yes. So they're all programming. So NetworkX can be used programmatically. GraphX can be used. The simple answer is yes. You can easily tie all these things together. NetworkX and GraphX are easy to package and work and to join and connect to each other because they're both programming packages. AWS Neptune is a package that offers REST APIs and other kind of APIs that your other two programs can actually communicate with. So you can actually create a system, a composite system that has all the three together.
Okay. Okay. Is anyone aware of general KG tool that one can use for vetting vendors? For example, sizing, licenses, type of pricing, etc.
At least I have not come across this. You would actually look at all these. There's no formula or any form or anything that I've seen out there. It's all on you to really evaluate it for your own use case.
Yeah, I mean, again, I think at the risk of pushing my own ideas here, I mean, if you're going to vet vendors, you're probably going to specify some kind of rule-based knowledge that you will use to vet them, right? Again, I'm not sure if this problem is more appropriate for machine learning because you probably don't want to vet vendors based on what you did in the past, right? You want to make a conscious decision as to why this vendor is good for you. And that's the kind of knowledge you would want to explicitly code in your program, right? And we've talked about examples of this throughout the course when we were talking about the knowledge graph inference. We had this conflict of interest example, right? So where you're checking conflict of interest and you write rules to say what conflict of interest is, right? So to me, it seems like a problem which has a rule-based component to it.
Yeah, that's a good point. Cool. So, okay. Do you want me to read the questions?
Yeah, I can read it. I can read it. Anjan is saying, well, where can we read about the modern way of building software using open source components?
All over the place. So I'll tell you how I personally try to catch up, and then maybe Vinay, you and Mike can also give your ideas about how you personally catch up on all these new software. So subscribing to a lot of newsletters, looking in technology news, looking at GitHub all the time. They have a feature called trending. You can sort by stars. They have every week they have a module there which tells you all the trending software in the last week. On LinkedIn, there's a guy called Philip Volley who curates and in his LinkedIn feed he mentions all these awesome software. So I follow him. So there are, I think, all these different ways. Maybe Vinay, you and Mike can suggest a few ways.
Well, my suggestion is keep coming to the Knowledge Graph seminar. No, I mean, I think you answered the question really well. I don't have a better answer to add to that.
Mike, what are your ways?
I'm more, since I'm perhaps more in the research community, I'm mostly concerned with reading the literature and trying to figure out what new ideas to incorporate and not tracking as nearly as extensively as you and Vinay are the capabilities that are being put out in these various different repositories like GitHub. So I learned about them by, as Vinay says, by listening to you guys, to the various different speakers we've heard here, and I've got many mailing lists that seem to have found their way. Messages seem to find a way into my mailbox. So that's it. But yeah, I don't have anything more to say than what you guys have already said.
Right.
Okay.
So then there's a question: are there any benchmarks for knowledge graphs?
So I've seen a couple of them. For compute, I've seen a lot of different packages comparing their numbers on calculating page rank, for example, which is like a computation over the graph. But for building graphs, I'm sure there are like maybe something around Wikipedia or something. But nothing comes to my mind.
Yeah, I mean, I think they are mostly task-specific benchmarks, right? So if you're doing entity linking, then there is a benchmark for that. If you're doing relation extraction, and within relation extraction, there are many different variations of what kind of relation you're extracting. And each of them has its own data set, its own benchmark. I mean, there's a whole bunch of stuff there. Then if you are just interested in the raw performance of doing inferencing on knowledge graphs, that would require different kinds of benchmarks, right? So it's a whole space, and I haven't done a survey of those, right? I don't know who else has.
Yeah, good question. I don't know.
What's the most frustrating, annoying, time-consuming aspect of building a knowledge graph? Any stories from your experience?
I think the first part where you join these lists and then you extract information from these unstructured text, that takes a really long time, and it is not at all 100% accurate. So that is a guarantee that you can be 100% accurate that you will not be accurate. So what do you do then? How do you get the feedback loop in? How do you get your users to correct for that? How do you get explicit feedback, implicit feedback? So I think there are all sorts of challenges when building knowledge graphs. So this is what I've encountered. How about both of you?
Yeah, I mean, I agree that it's a noisy process, right? It's a noisy process, and you have to deal with scale, and it can be frustrating, right? To ensure that you are getting the accuracy you desire. And people tend to claim that everything can be done automatically, but in practice, it is not possible to do that. And for me, that's the most frustrating part, where people advertise their solution as fully automatic, whereas it actually is not. I mean, you still have to do lots of manual work, and they don't tell you about that.
Yeah, I agree. What about, personally for me, one thing has been like learning these different query languages for graphs. Like SQL was quite intuitive, etc. But these query languages that I've encountered for graphs have been a little bit challenging to learn and a little bit non-intuitive. What are your impressions on that?
Well, I think from whatever little I know of Cipher, it's not bad. I think Cipher and Sparkle, they are both pretty good, I think. I mean, they are triple-based languages, and I think they have a nice formal translation to SQL if you want. So for me personally, query language has not been the challenge for graph systems. Maybe because I have reasonable theoretical grounding in how the languages are put together, but yeah.
Okay.
Can you all please share insights on a good process end-to-end involving automation and manual curation for launching a new KG-based system? Yeah, it's a good question, but it's also a very broad question, right? I'm not sure if there's a formula on how you do it, right? A lot depends on what data you have, what problem you're trying to solve, how much resources you have at your disposal. I mean, I'm not sure if there's a cookie cutter solution to this question.
Yes, I agree. And then, yeah, it's very messy. And the things that we covered in the lecture a few minutes ago, and then how to get the users involved and keep your graph fresh, etc.
Mm-hmm.
So no easy formula.
Okay, so then there's a question, can people use GraphDB for graph computing? GraphDB is OLTP, graph computing is OLAP. Can you use one for the other? And I think Naren's slide explained this very clearly. And I think what I got from Naren's slide was that if you are interested in things like asset properties, you want to do transactions, right? Then you want a graph database because you will be changing your database, right? And you can't, it's not a pure read-only operation, right? Whereas OLAP or analytics, they are primarily read-only operations. You're not making updates, right? So clearly, if you wanted to do updates, you shouldn't be using OLAP, right? And if you're using OLAP, if you only have reads, potentially you can do optimizations, which you won't be able to do if you have to do both reads and writes, right? So clearly you can use an OLTP system for OLAP. Most likely it won't be as fast because you are having to optimize both reads and writes. Okay.
Yeah, and I have a comment on that. There's a embedded in this comment is a sentence which says, it seems graph DBs do not have much use. So let's say you want to do just traversal of links or something like that. You can quite easily implement it in a SQL database, but then you have to index some of those columns and then match, and actually you have to do the traversal yourself. If you look within how a graph DB is designed, right in the node, there are the C-like pointers to the next node. So all that traversal becomes super fast. So in applications where you have to really traverse these nodes really fast, graph DBs are very, very useful.
Yeah, I think we covered this in our lecture too, where I compared it on a very simple example, what it would look like if you were modeling it using graphs versus modeling it using SQL, right? And the SQL queries turned out to be a little bit bigger or longer, right, as compared to the queries in graphs. And I also said that, well, you could write a translator from graph queries into the relational queries. And in fact, the system that relational.ai people are building is in that spirit, right? So, I mean, their underlying storage is purely relational, right? But they still accept graph-like queries. The language admits graph-like queries, so you can have compact queries. And they have implemented special join algorithms that do very well on the graph queries. Okay, so which question do we want to take? Actually, there are also lots of things in the chat.
Oh, okay. Cool. So even I can read.
So the chat was fairly empty.
Oh, QA. No, it's in the QA box.
Right.
Okay. Any thoughts or tools that might help with incremental adoption of KGs rather than taking a big bang approach?
Oh.
So I would overall say, if it's a simple application of knowledge graphs where you don't have to do too many operations, graph-like operations, just traversal or something like that, just use a SQL and implement all the traversal yourselves. You'll not be able to do a lot of things like then compute shortest path, do all the graph kind of analysis, subgraph, page rank, community, but it all depends on, maybe you have a simple application that you want to create.
And I think the other way to say that is that if you have a problem where traditional solutions are failing, then look at a graph system. I don't think it makes sense to push a graph-based system just for the sake of pushing a graph-based system, right? if you're working with relational system and it's working for whatever problems you have at hand, just keep using it, right?
Yeah, use relational, use search engines, somehow find clever ways to use search engines. If you can get by, just do that.
Right.
So there's one here. Vinay shared a great UI framework for the KG-based systems. For user experience, are there good templates in D3? I don't know specifically for that, but D3 has a good set of visualizations which are interactive. And you can just take a look. There's a very good website by the author, and the author has curated a large number of examples from different people that send their ideas. So you can actually go through and then you'll get a pretty good idea.
So somebody's saying, what's a good set of tools for a non-expert to use for building a knowledge graph? I mean, I'm not sure if a non-expert can easily build a knowledge graph. No, that's why we have courses on this topic. And again, non-expert it's a very broad field. I mean, there are non-expert programmers and non-expert CS people versus English majors, right? So I don't know what kind of non-expert we are talking about here.
Yeah, and it depends on the data sources. Let's say you have lists, you have 5 lists that you want to join together and create a knowledge graph. Some of the packages that I mentioned today to join lists, they have actually UI. They have a UI, and then you can have the non-technical user actually join those lists, etc. And once they are joined, I think then you could load them up into a knowledge graph.
Right. So drawing a schema is tedious. I have hundreds of tables. Is there a tool to draw schema from the data? Well, I'm sure there is. I'm sure there are people out there who are who are visualizing relational schemas. They are mapping it to some kind of a ER scheme or right. So, Diane, are you aware of any?
No, I've seen all those ER diagrams, etc., of schemas, but learning that automatically from data, I do not know.
Okay. So I propose that we conclude this segment.
Okay.
I think we've taken most of the questions, substantive questions. I need about 15 minutes to do my part. Yeah.
Sounds good.
And that will take us to like 5:48 and 5:38, and then we still have five or so minutes for question and answers. Yeah.
Sounds good.
Okay. So let me get my slides. All right. So this is the last week. And during this series, we started off by talking about what is a knowledge graph. We discussed the data models, the query languages. Then we had a few lectures on how we go about creating a knowledge graph. We had a segment on how to reason with the knowledge graph, how to access the knowledge graph. We saw lots of different applications. Today, we've been talking about implementation tools. And now we are at a point where we want to conclude, and we also want to look a little bit towards the future, which we will be doing mostly in Thursday's session. So in next 10 or 15 minutes, I'm going to try to synthesize and try to address this question of how do knowledge graphs relate to AI. As I was saying earlier, I have seen a lot of people just give this knee-jerk reaction that there's nothing new about knowledge graphs, and knowledge graphs have been done in AI for a very long time. So This is just old stuff rehashed. And my own view is that the fundamental theory is fundamental theory. It's not going to change. And that's why we define a knowledge graph as a directed label graph, which has been around for a long time, right? There's nothing new about that. But yet there is something new, right? And that's sort of what I'm going to try to convey in next 10 to 15 minutes. And some of these thoughts are synthesized based on various talks that we had in the series last year, and they are also influenced by some of the things that have been said in lectures during this year's series. And I've basically synthesized them into three main points, three big points. One is knowledge graphs have become a test bed for AI. There is this new discipline, which we are now calling graph data science, which exists now, which didn't used to exist. And then there are some interesting observations about how do knowledge graphs fit in the ultimate vision for AI. Okay, and I'm going to go deeper into each of these three. Knowledge graphs have a two-way relationship with AI. And the way that works is, in a way, knowledge graphs enable many AI applications. That is, by using knowledge graphs, AI applications perform better, they get better. And in the other directions, the AI algorithms, they can be used to create knowledge graphs. AI is helping us build knowledge graphs. Let's look at each of these sides of the relationship a little bit more closely. So the personal assistants like Alexa and Siri and Google now, they all use knowledge graphs. And it's sort of well accepted that if these assistants can use knowledge graphs, they can get more things done. We also saw that knowledge graphs are playing a central role in recommendation systems. We have heard about the Amazon product knowledge graph, and we've seen that how it is used in their commerce website, and we see its effect. You know, it's able to suggest with some degree of accuracy as to other things we should be interested in. We also heard from Shashi early on in the series when he talked about how knowledge graphs are used for improving the search results. And in fact, in my first lecture, I had talked about how a graph like Wikidata can be improved, can be used to improve the search results. So these are all examples that knowledge graphs are enabling these AI applications. They're enabling these AI applications to function better. And all of these applications, I would claim, they are novel. These applications definitely didn't exist 50 years ago, right? It's more of like a phenomenon that has come about in the last 10 years. In the other direction, the knowledge graphs that we are using, they are being built using AI algorithms. So for example, we talked about schema mapping and entity linking, and especially for doing entity linking, we talked about active learning techniques. We were doing active learning of random forests, which is an AI technique, but it is helping us build the knowledge graph by fusing the entities coming from different data sets. Entity and relation extraction from text, they use NLP technology. And we considered the use of language models during the course for doing both entity and relationship extraction. Then things like data cleaning, anomaly detection, inference, question answering. These are operations on the knowledge graphs. So for example, the inference and question answering, to do question answering over knowledge graphs, we are using natural language processing algorithms. And in a way, those AI techniques are helping us make better use of these knowledge graphs. So that's sort of a two-way relationship that has kind of developed between knowledge graphs and modern AI algorithms in a way that they are both feeding off each other. So that was my first point. Okay. So the second point is the emergence of this new field, which we are calling graph data science. And this is driven by two different trends. One is modern organizations have huge amount of data, be it search engines, e-commerce websites, banks, grocery stores. They are tracking lots and lots of data, and the businesses are very interested in deriving knowledge from the structure of the data for a variety of tasks, for recommending products, for doing marketing, for doing business intelligence, whatever. So the desire to make use of this data has spawned this field that we are calling graph data science. And many components of graph data science, they are not new. Okay, so things like graph algorithms, graph visualization, graph queries, these are topics that have been worked on for 30, 40, 50 years, or maybe even longer. But their confluence in the context of the availability of data has presented some new things. And first and foremost, there is increasing use of machine learning for making predictions, which has led to this subspecialty called analytics. But these machine learning algorithms, they cannot work in vacuum. You need some knowledge about the domain to figure out what features should be in your model. And then you also have to understand how your model is responding to these features, right? So which is a fairly unique skill set, which in older times used to be possessed by knowledge engineers. But in the current times, you have to be able to do feature engineering, and that requires some real skill, both in the domain as well as in the understanding of the algorithms. And then there is a need for a new kind of data exploration. Like when you are dealing with a very large amount of data and you want to present it to the user, there is a skill needed to design proper user experience for it so that the user doesn't get lost in it and they are able to make effective use of it. And the confluence of these three fields, analytics, feature engineering, and data exploration, this is what we are calling graph data science. And this kind of skill is in very high demand in the industry. I know a lot of organizations who are hiring like crazy for graph data scientists. And we anticipate that this skill is going to remain important and maybe become even more important in the future. So that was my second point. Now, the third point is knowledge graphs for AI. And as I noted earlier, knowledge graphs have been used in AI since the beginning. The earliest knowledge graphs were semantic networks. And then some people said, no, we have to associate more semantics with the semantic, or we have to formalize the meaning of semantic networks. And that spawned this whole field of description logics. Some people who cared more about the tractability of reasoning, they went in the space of description logics. There are folks who focus exclusively on rule languages. They're not necessarily concerned with the decidability of reasoning. But both description logics and rules are a step up over semantic networks by adding rigorous logical semantics. We also have a need to deal with uncertainty in the real world. And to deal with uncertainty, the earlier models in AI were simple Bayes nets. But more recently, there has been a substantial development of Bayes nets, which are currently known as probabilistic graphical models. So all of these representations, they have their roots in directed label graph representation, and they have been worked on for a long time, and they are fairly mature. But representation is only one side of the story. We also have to be able to build the representation. And for building the representation, the early approaches were based on a person sitting down and writing that piece of knowledge, known as knowledge engineering. But there were also techniques to automatically learn symbolic knowledge called inductive learning. And more recently, we have seen the heavier use and success of machine learning methods. So that brings us to the question, what has changed? What is new? And in my mind, there are three differences between the classical work on these topics versus what's happening now. And those three differences are scale, bottom-up construction, and mixed modes of construction. So by scale, I mean that even if what we are building now are semantic networks, but these are really huge, right? We said that the Wikidata knowledge graph, even if you say it's just a semantic network, it has 80 million or so objects or 3 billion or so triples, right? We've never had a semantic network approaching nearly that much scale. So the scale is really different in terms of what we are seeing in the knowledge graphs of today. The second point is the bottom-up construction. The early work in AI was driven by this desire to do a top-down design. Let's sit down, let's carefully design what we are going to model, and then we are going to populate our model. But what we see happening these days is let's see what data we have. Okay, let's see what data we can collect, and then on that we will run our machine learning or we will run our NLP, and we'll see what kind of entities and relations we can extract. And once we extract them, then we'll figure out what kind of conclusions or reasoning we can draw from it. And I would say there is a lot more of this bottom-up kind of work going on these days than it used to be. I mean, not that in the earlier days there was no bottom-up work, but currently there is preponderance of work is focused on doing bottom-up analysis or data-driven analysis. And three, the knowledge graphs of the sort we are seeing today, they are being constructed using mixed modes of construction. I mean, there is clearly some manual effort or traditional knowledge engineering, but there is heavy use of automation. And that's what's helping us get to the scale, right? It's not just one strategy or one method to build the knowledge graph. We are using a combination of methods to build the knowledge graph. Having said that, these three are the big differences between knowledge graphs of today versus what was happening a few decades ago. It doesn't mean that we can't have AI at small scale. You know, there are a lot of problems which are small scale, but they still require intelligent behavior. It doesn't mean that top-down design is not important. Even if we build our knowledge graph in a bottom-up manner, but we still have to think about the semantics of what we are learning, what conclusions we can draw from it. And that does require some top-down design. And the fact that some of the knowledge we can learn automatically doesn't mean that we shouldn't be able to write down what we know, right? Anything we know and understand, we have to be able to express it in a computable form. And the importance of that doesn't go away just because we are able to learn that knowledge. So in AI, you know, people have had this vision of systems which have these visionary capabilities, like systems that have complete models of a domain, systems that can formulate hypotheses, perform high-level cognitive tasks such as designing experiments or providing explanations. We're still not doing very well. We're not able to build systems like that. And it's unclear if knowledge graphs are really sufficient for building systems like those. Knowledge graphs happen to be at a point where they are able to provide us just enough representation power which is needed for the kind of applications we talked about, like search and data integration and NLP and vision. It's just at a point where it matches what's needed, but it is not clear that it is sufficient for where we eventually want to go. And that's really going to be our primary focus for next week, not next week, for Thursday. So on Thursday, we will have two visionaries from our field, Professor Jim Hendler and Dr. Doug Leonard, who will give us their perspectives on where the future is with knowledge graphs and how knowledge graphs can help us go beyond the current state of the art and towards things that are not possible today. So with that, I will conclude what I had to say. We can take few more questions and comments, and then we'll end today's session.
Cool. So there is one question.
Okay.
So great insight and guidance. Enjoying this learning very much. Parsing and looking for the question. Oh, okay. So
that's just a comment from
okay.
Anand. So thank you very much. Yeah, so then there is the question about personal knowledge management, and there are hardly any tools available for that. Well, I used to be involved in this project called Kalo, where at SRI, where we were, where our charter was to build a system for personal knowledge management. And in fact, our schema was a knowledge graph which had things like contacts, emails, documents, projects, and people. So we had 5 or so different classes, and we built a version of that, and the system we had in the research project had a lot of interesting capability, only fraction of which has been productized. But somebody saying, oh, they're still constrained by the hierarchical structure of folders. Yeah, I agree with you that somehow the state of the art in the products doesn't move very fast. And having been in that research project, I know that the kinds of ideas we were pursuing in the research project, only 2% of that has actually made impact on the products. I don't really know what to say to that. Part of it is the extent to which the startups are able to pick up ideas from research and actually bring it to the market, right? Naren, Mike, do you have any perspective on this?
Yeah, I agree. So I think you try out a lot of ideas very quickly, and especially in the space of AI, I think we're definitely very, very far away from having these products that are very intelligent and then will operate in any kind of circumstance. I think the trick is to figure out a very, very narrow use case. And also the whole product design has to come out really well. And that takes all the effort.
Yeah, I think the comment is that the end users are normal people, not scientists, and the tools you mentioned aren't useful for that use case. And I agree. I think this course is really designed for programmers, right? We had one session on HCI and user interface design, but that is a completely different mindset and scale and completely different problem.
So I think a lot of end users, not scientists or engineers, are likely to benefit from domain-specific special purpose knowledge management systems built by those scientists and engineers, and not general purpose personal knowledge management tools. Even the Halo thing was had specific classes of information that you were managing, and so it may not be that general purpose personal knowledge management tools are in as great a demand as the commercial ones are.
Yeah.
Let's see, there's a couple more here. Oh no, okay.
Yeah, again, I think there is ton of work on personal information management systems. I know Alon Halevi has had a lot of papers on that topic. He's the closest to the sort of the database type things that I'm familiar with. And I'm sure, there is within HCI, there are a ton of people working on office automation and personal knowledge management tools.
Well, is that what personal knowledge management is? Office tools? Is that I'm not sure whether that was the only thing that was being covered there in that question. I agree with you about that particular subfield. That's obviously an area where there may be some commercial value for.
Right.
It's a question about knowledge scientists here, and I suppose it's different from knowledge engineers, though I'm not quite sure I got the full gist of that.
Yeah, I mean, I think the knowledge scientist concept was pushed by Yuan Sequida. He was one of our invited speakers last year. I think he was in lecture 2.
Yep.
So I mean, I encourage you to go listen to his arguments for knowledge scientists. But from what I recall, he was saying that when you're doing this schema mapping, it's not really possible to do it automatically. You have to know a lot about the domain. And that's the skill set he was calling as a knowledge scientist, where it's not just crunching data, it's also being able to model the domain and understand the semantics of the domain and then being able to capture that. You don't agree, Mike? Or
No, I'm just, I'm kind of the odd man out in this whole knowledge graph world, where I think the bar for what makes intelligence has descended very low. If what we consider is Siri and Alexa and recommender systems to be intelligent, I mean, they're useful, no doubt, and I like them, but I'm not going to have myself be diagnosed necessarily by Alexa or Siri. I definitely would like to have medical research done by machine learning programs, or at least take advantage of that, but I still want to have a doc there for the time being. Or such, what makes intelligence has gone down. And my concern is not big data science, which produces very shallow and weak conclusions, but rather small data science. The Sherlock Holmes of the world that can take 2 little or 3 little facts and tell you who done it, using knowledge, large amounts of knowledge to form conclusions from very little amounts of data, seems to me more in line of what AI used to be.
right.
So
yeah, so I mean, I think that's exactly why I acknowledge that point of view in one of my slides, right?
Yes,
So like,
right.
Just because you're doing big data doesn't mean that that's the only way to get intelligence. There is small data intelligence too, and that's equally important, right?
Yeah.
And also I think that there was this question, and this is a discussion we've had amongst ourselves, is whether to even touch the overlap between knowledge graphs and AI. In this course, we have covered certain body of algorithms and techniques which have useful for certain classes of applications, right? And that is interesting in its own right? No, you don't agree?
No, it's inevitable, because machine learning right now is so dominant and so producing, so productive at the moment. We have to talk about the relationship and knowledge with AI equals machine learning. And of course, knowledge graphs are a key part of that, as you just argued very, very eloquently. So I think we have to make that connection. The question is whether that is the AI of old or not. That's, I think, the schism that has arisen and has not really been resolved yet. But I think you spoke to that very well with your slide towards the end.
Yeah, I mean, I think that people will debate about that, right? And especially if you present that view to people who grew up in the machine learning era, they would probably say, what the heck are you talking about? Right. So that challenge is definitely there. And I've actually experienced that firsthand, right? Yeah. And because these days, if you talk to people about representation, what representation means is a vector. That's what representation means. And that's the only representation people know about. Yep. All right, so we have roughly 1 minute. Any final remarks?
Looking forward to Thursday. Don't miss Thursday. Thursday's going to be good.
Yeah, Thursday is going to be good. We have 2 luminaries. Jim Hendler, who is famous for speaking little semantics goes a long ways, and Dr. Doug Lennett, whose life has been about being at the maximal end of semantics, right? So it should be a great conversation. So thank you all very much, and we'll see you on Thursday.
Thanks to the speakers. Appreciate it.
Thanks, Narayan.
Welcome.
Bye.
Okay, bye.